All right, let's talk about integral calculus. Now, I know that phrase can sound a little intimidating, but stick with me. I'm about to let you in on a little secret that turns this whole thing from a mountain of memorization into a super simple logical puzzle. Let's dive in. Does this look familiar? You just got your head around derivatives, and bam, you're hit with a whole new set of rules for integration. You've got new symbols, new formulas. It can seriously feel like you're starting all over again. And that feeling of frustration, totally normal. You see that long squiggly integral symbol, the little dx at the end, and of course that mysterious plus c that you're always told not to forget. It can feel like you've just run into a giant wall of new information. But here's the thing, you already have the key to smash right through it. You really don't need to memorize most of this stuff. And that brings us to the big idea for today. Forget that long list of new rules for a second. There is one single powerful concept that unlocks basically everything you need to know about integration. And the best part? It's been hiding in plain sight this whole time. This is it. This is the secret. Integration is just differentiation backward. That's the whole idea. Think of differentiation as doing something, and integration as just hitting the undo button. It's all about working backward from an answer to figure out what the original question must have been. So look at how this plays out. Over on the left, you start with a function. You differentiate it, and you get a derivative. Easy enough. Now, on the right, you take that exact same derivative, you integrate it, and you end up right back where you started. It's a perfect loop. And that plus c? Well, think about it. The derivative of any constant number, like 5 or -20 or a billion, is always 0. So when we go in reverse, that constant disappears. We have to add the c to remind ourselves that some constant could have been there. Okay, so that's the theory, but let's actually prove it. We can literally build the rules for integration just by using the differentiation rules you've already learned. Let's see how this works with a couple of key examples. We're going to start with an old friend, the power rule. We all know how to find the derivative of x raised to some power. We're going to use that exact knowledge to build the integration power rule from scratch. Okay, let's just walk through the logic here step by step. First, we start with what we know. The derivative of x to the power of n plus 1 is n plus 1 times x to the power of n. Got it. Now, for step 2, we just reverse it. Since integration is the opposite, the integral of that answer we just got, well, it has to take us back to the original x to the n plus 1. It's a two-way street. Step 3 is the clever part. We only want the integral of x to the n all by itself. So what do? We just use a little algebra and divide both sides by that constant, n plus 1. And that's it. Step 4, we've just derived the power rule for integration without memorizing a single new thing. And this logic works for everything. You know the derivative of e to the x is just e to the x, right? Well, then you automatically know its integral is e to the x. You know the derivative of sine x is cosine x? Then the integral of cosine x must be sine x. And check out this last one. This is a perfect example. We know the derivative of cosine is negative sine. So if a problem asks you for the integral of positive sine, you just think backward and realize, the original function must have been negative cosine. It's really just a logic puzzle. All right. Let's really put this thinking in reverse idea to the test. We're going to take a standard calculus problem and solve it without looking up a single formula, just by using this inverse thinking. So here's our problem. We need to find the integral of x cubed plus 2e to the x minus 1 over x. Now this looks like it needs 3 different formulas from that big, scary list. But really, it just needs us to ask 3 simple questions. Let's go term by term. For that first piece, x cubed, we just ask ourselves, okay, what function, when I take its derivative, gives me x cubed? Well, the power must have started 1 higher, so at 4. But the derivative of x to the 4th is 4x cubed. We just want x cubed, so we need to divide by that 4. So it's x to the 4th over 4. Next up, 2e to the x. This is the easy one. What's the derivative of 2e to the x? It's just 2e to the x. Done. And finally, that negative 1 over x. We know the derivative of the natural log of x is 1 over x. So to get a negative 1 over x, the original function must have been the negative natural log of x. See? We just solved each piece by working backward. And there it is, our final answer. We put all those pieces we figured out back together, we add our trusty friend, plus c, and we're done. We got the right answer, not by remembering a formula, but by actually understanding the connection between these two big ideas in calculus. So what's the big takeaway here? This isn't just a clever trick. It's a fundamental shift in how you look at the entire subject. Thinking this way, turning memorization into reasoning, well, that's like unlocking a new superpower.
So let's quickly recap what we've learned. First, integration just undoes differentiation. They're two sides of the same coin. Second, you can use the derivative rules you already have down cold to solve tons of basic integrals. Third, this isn't about finding a shortcut. It's about shifting from just memorizing to actually understanding what's going on. And last but not least, never, ever forget to add the plus C.
And that leaves us with one last question. This idea of thinking in reverse is a powerful tool that goes way, way beyond a math class. Whether you're debugging code, planning a trip, or trying to figure out a mystery, asking what had to happen right before this can unlock solutions you'd never see otherwise. So, think about it. What's one problem in your world you could try to solve by working backward?